In the last few segments, we defined the topic of stereoisomers, and we talked about how to recognize enantiomers. We talked about how to identify chiral centers, that is, carbon atoms that have 4 different groups bonded to it, and we looked at drawing structures that are related to one another as enantiomers. Now, it's not always convenient when we're trying to convey information about organic molecules to draw out the structure every single time. And so that's why we learned in previous chapters about coming up with IUPAC names for molecules. The thing that we haven't talked about yet is when we make the structures of IUPAC molecules, how can we, within the IUPAC name, specify the stereochemistry of the molecule? Because the stereochemistry of the molecule certainly has important impacts on how those molecules interact with, for example, biological targets. And so we need a way to, on paper, specify what the configuration is of a molecule. And what we're going to look at in this segment is how we go about specifying the so-called absolute configuration of a molecule using RS stereochemistry assignments. R and S are the terms that we will use to describe the 3-dimensional orientation of any chiral carbon within a molecule. So if we were to look at the structure that we see here in the lower right corner, we can recognize that there's 2 chiral carbons. Those chiral carbons are carbons with 4 different groups bonded to them, here and here. And if we have wedges and dashes shown around those chiral carbons to indicate the orientation of the different atoms, then we can assign each of those chiral carbons as either an R chiral center, which specifies one of the possible stereochemistries at that chiral carbon, or an S chiral center. So we can do that for both of these chiral centers within this molecule. And the purpose of this segment is going to be to walk you through the steps required to assign a chiral center as R or S, because being able to properly assign chiral centers can be the difference between life or death, literally. It can be the difference between a molecule that is able to cure a disease versus a molecule that will kill a person. So we need to be able to identify the absolute configuration of molecules. So let's go ahead and get started with that. First off, you will want to have handy the handout that goes along with this material, which is this handout on assigning absolute configuration of chiral centers. And we're going to assign the absolute configuration of each chiral center that we find within a molecule, where we have wedges and dashes at that chiral center to allow us to establish that. We need wedges and dashes, otherwise we're not going to be able to tell what the 3-dimensional orientation of that group is. So after you've gone in and picked out your chiral centers and seen the ones that have the wedges and dashes associated with them so you can assign R and S, we're going to go through the 3 steps listed here to specify the RS chirality of each chiral center. So first and foremost, we're going to look at that chiral carbon and we're going to look at the 4 groups that are bonded to that, or the 4 substituents bonded to it, and we're going to rank those 4 groups. We're going to do that by looking at the atoms that are directly connected to the chiral center. So we're focusing on atoms here that are directly connected to the chiral center, and we're going to rank those based on atomic number, where a higher atomic number means a higher rank. So let's go ahead and get started with an example problem that illustrates this point, and we're going to do it for this example problem up top here. And I will go ahead and redraw that just for convenience here. So we're going to go ahead and draw in our carbon chain, just repeating what I had drawn up top there in the title area. So go ahead and put in our alcohol functional group, and then we have this isopropyl group that I'm going to draw in right here. So we're going to go ahead and use this as our example to get started on the process of assigning the absolute configuration. So we're going to rank all 4 atoms that are directly bonded to a particular chiral center. The chiral center I'm going to pick out to focus on is this one right here for starters. We will then go back and assign the chirality of our other chiral center right here as well. But for now, we're going to focus just on that chiral center that has the hydroxy group bonded to it. So we have to ask, what atoms are directly bonded to the chiral center? The atoms that are directly bonded to the chiral center is with a star, and remember that whatever piece of the tetrahedron is missing, we can fill in wherever we want, and that's going to be our dash to a hydrogen here. It's because we have a wedge, we have 2 lines, so therefore the missing part of the tetrahedron is the dash. All right, so now we need to go in and rank the 4 groups based on atomic number of the atom that is directly bonded to the chiral carbon. The chiral carbon's in blue, so it's directly bonded to that green H, directly bonded to the green O, directly bonded to the green C. That would be a carbon of a methyl group. I'm just filling in the carbon directly to show the 4 atoms that are directly bonded. And then we'd come over to the left and we'd have a carbon as well. So we rank these based on atomic number. So we look at the periodic table, and the atom that has the highest atomic number out of these is going to be your oxygen atom. So I'm going to put a number 1 there because we're ranking in order from highest atomic number to lowest atomic number. So number 1 is oxygen. Number 4, our lowest ranked group, is that poor hydrogen atom there. There's no group that's lower ranked than a hydrogen. So now we have a little bit of a conundrum because we have 2 carbon atoms left to assign, here and here. Those 2 carbon atoms are definitely not part of identical groups, and so we need a way to rank those relative to one another. The way that we are going to rank them relative to one another is we're going to ask ourselves what each of those 2 carbon atoms is bonded to next in line, and we are going to choose what of those groups has the higher atomic number. So the carbon atom on our right here, I'm going to go ahead and change my color designation here to red to specify that now we're looking not at the atom that's directly connected to the chiral carbon, but we're looking 1 atom further down the chain. So the carbon atom that we had here in green is directly bonded to 3 hydrogen atoms going away from the chiral center. So it's going to be bonded to H, H, and H because that's a CH3 group. On the other hand, if we come over to here, this particular carbon atom is directly bonded to carbon, carbon, and hydrogen as we go away from the chiral center. And the carbon that we're talking about is the carbon right here, and the carbon right here. The hydrogen we're talking about is the hydrogen that has to be there to fill that carbon's octet. So again, these 3 groups we're talking about, C, C, and H, are all working away from the chiral center. So go ahead, and now in order to determine the relative ranking of our carbon atom circled on the right versus the carbon atom highlighted in green on the left, we ask ourselves what's bonded to each of those carbons as we go away from the chiral center. So the one on the right is bonded to 3 H's, the one on the left is bonded to C, C, and H. Carbon is higher ranking than hydrogen because that has a higher atomic number, and so therefore the group on the left is the higher ranking group. So I'm going to plug that in as carbon number 2. We already established that the OH group was ranked number 1, so this is ranked number 2. Number 3 is going to be this methyl group, and number 4 is our hydrogen atom. So with that, we're taking care of step 1 here. We've ranked all the substituents that were directly bonded to the chiral center. We started off by looking at the 4 atoms that were directly bonded to the chiral carbon and ranked those based on higher atomic number, being higher ranked. And then for places where we saw that the atoms connected directly to the chiral carbon were the same, such as the 2 carbons here, we then went one more spot down the chain to look at all the atoms that that particular carbon was bonded to until we found a point that was different. And in some cases, you may have to go down the chain several carbon atoms to get to a point where you can differentiate between the 2. But if the chiral carbon is actually a legitimate chiral carbon, you will always find a place where you can tell the 2 chains apart, because if they're identical, then the chiral carbon is not actually chiral. All right, so carrying onward here, what we're going to do is, in step 2, we're going to rotate or orient the molecule so that the lowest priority group points away from you. It's a dash rather than a wedge or a line. So we got to orient the molecule so the lowest priority group points away from you. In other words, that lowest priority group is a dash. All right, so in the case of this molecule, when we're identifying the chirality of that carbon that we've put the blue star on, our lowest ranked group, fortunately for us, is already pointed away from us. We have the hydrogen atom on the dash. So therefore, we've already taken care of step 2 here. We will do some examples later on where we will have to do some rotation or other manipulation of the molecule to get that lowest ranked group oriented correctly. Now what we need to do in step 3 here, with my highlighter, I'll go ahead and mark that. In step 3, we're going to draw a circle that starts at the highest ranked group and moves through group 2 and then on to the 3rd highest ranked group. So we're drawing a circle here to go from group 1 to group 2 to group 3. So we do 1, 2, 3. And we ask ourselves then to go from 1 to 2 to 3 in order whether the circle that we drew runs clockwise or whether it runs counterclockwise. So if it runs clockwise, we describe the molecule as being R, much like the correct clock or the right clock runs clockwise. And if the circle runs counterclockwise, we call that the S clock, or one way to think of that is the stupid clock runs counterclockwise. So we're going to go ahead and look at this molecule, and going from 1 to 2 to 3 takes us in a counterclockwise circle. So therefore, we would describe this particular molecule as having the S configuration. So I'll go ahead and put S there to specify that that chiral carbon is an S chiral carbon. We also need to go in and specify the stereochemistry for the other chiral carbon in this molecule. So that's what we're going to do now, specify the chirality for that chiral carbon that is also in the molecule, the one that's bonded to the isopropyl group. Just so that it doesn't look quite so cluttered, I've redrawn the molecule from up top, and now what we're going to do is specify the chirality of this chiral center right here, the one that we didn't already specify. We're going to go through these 3 steps again for assigning absolute configuration to come up with the assignment here. So first things first, we need to go in and rank all of the groups that are bonded to the chiral center. So our groups bonded to the chiral center, I'm going to put in green the atoms that are directly connected to our chiral carbon. Directly connected to the chiral carbon, we have this carbon right here, the one right here, the one right here, and then implied is our hydrogen, which this time has to be on a wedge because that's the part of the tetrahedron that is missing. Okay, so now we need to rank those 4 groups that we've shown based on the first atom away from the chiral carbon. So looking at those 4 atoms, carbon, 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 hydrogen, we rank those based on atomic number, and based on what we see here, all we can really rank at this point is the hydrogen is the lowest ranked of those because it has the lowest atomic number. Now we need to differentiate between these 3 carbon atoms. The way we do that is by looking at what each of those carbon atoms is directly bonded to. So what I'm going to do to show this is a shorthand notation where I put carbon, which is reflective of that green carbon, and then I'm going to put in parentheses here the 3 atoms that that carbon is directly bonded to other than the chiral carbon. So our carbon in green is directly bonded, and I'm going to put these in order of decreasing atomic number to keep myself organized. That carbon is directly bonded to an oxygen. It's directly bonded to a carbon of that methyl group at the very end, and it's directly bonded to a hydrogen that isn't shown but has to be there to fill the octet. So that carbon that I've got the line going to is bonded to O, C, and H. We're trying to keep organized here about what each carbon is directly bonded to so that we can appropriately assign the rank of it. We come down here to our carbon, right here in green at the bottom, and we ask ourselves that same question. What is that carbon directly bonded to other than looking back at the chiral carbon? So that carbon is directly bonded to carbon of one of those 2 methyl groups it's bonded to, carbon of the other of the 2 methyl groups, and it's also bonded to that unseen hydrogen there to fill its octet. So carbon, carbon, and hydrogen is what that carbon in green is bonded to. We come on over and do the same thing at this carbon atom. So this carbon atom, which I'm putting in green just to color code it the same as it is in the molecule, is directly bonded to each of the 3 atoms that I'm going to put in black. Those 3 atoms, going in order from highest atomic number to lowest, is going to be a carbon, and that's of the methyl group right here at the end of the molecule, hydrogen, since it's a CH2 group, and another hydrogen, since it's a CH2 group. So now what we will do is we'll take these 3 sets of assignments, highlighted in yellow, and we will choose which one of those has the atom with the highest atomic number. So in the upper right, we have oxygen showing up in our brackets. The other 2 possibilities just have carbons and hydrogens. So oxygen has a higher atomic number than carbon or hydrogen, and therefore that group is going to be the highest ranked group. So that group we'll go ahead and plug the number 1 on. Now what we need to do is rank these other 2 groups, and I'm putting the red line underneath. So on the right we have carbon, carbon, hydrogen. On the left we have carbon, hydrogen, hydrogen. So we look at these and we pick out where can we differentiate between them. So they both have carbon and carbon, so that we can't tell them apart by that. But the next step, we have either hydrogen or carbon. Carbon has the higher atomic number relative to hydrogen, and therefore the carbon over here is going to win. So this is the second highest ranked group. That leaves us with over here as the third highest ranked group, and we already said that the fourth lowest ranked group was our hydrogen atom. So now we come onward, since we've ranked the substituents, they're at step 1. Now we need to rotate or orient the molecule so the lowest priority group points away from us as a dash. So this is where this can get a little bit dodgy, because one thing that you can do is you can rotate this molecule around so that the highest ranked group points toward you and the lowest ranked group points away from you. So for example, we could just flip this molecule over. In other words, rotate around. So we could flip the molecule over. And it's totally legit to do that. Anything that doesn't require that you break bonds is a totally fine thing to do. And if you have a molecular model, you can show how when you flip the molecule over, how the atoms are going to change in position. So if we flip this over, what's going to happen is the OH group that was a wedge there toward the right is going to become a dash to the left. And our next position, which was our isopropyl group, rather than being a dash, is going to become a wedge. And then we have CH2, CH3, and those aren't chiral centers, so we don't need to worry about how we draw those. So what we've done is we've flipped the molecule over so that now the lowest ranked group, that is our hydrogen here, points away from us. And we don't care if it points as a dash to the left or dash to the right. Either or is totally fine here. And I'm going to go back in and just fill in my assignments that we said that this group was number 1. I'm just copying the information from the right lower side there. This was 2 and this was 3. And now that the molecule is properly oriented, what we can do is, since the lowest priority group points away from us into the page, we can just go in and draw our circle, going from 1 to 2 to 3. And going from 1 to 2 to 3 takes us in the counterclockwise direction, or the so-called stupid clock direction. So therefore, this would be defined as an S chiral center. So in the case of the molecule that we've used here as our example, we had 2 chiral carbons, and both of those turned out to be S. They could certainly have been any combination of R and S, depending upon what was shown as a wedge versus a dash in the molecule. So we've gone in and assigned the chirality at all 2 chiral carbons. And in the case of the second one, we did have to rotate the molecule around to allow us to properly do that, since the definition of assigning this absolute configuration requires that the lowest ranked group be pointed away from us. Here's another hack to help you in doing the assignment of RS stereochemistry in cases where the lowest ranked group is not pointed away from you, but instead is pointed toward you. So the hack here is that if we were to take the structure on the lower right hand side here, and I'm just going to redraw it since I've scribbled all over it to make it a little bit easier to see here. We're going to fill that in like so. I'm going to fill in my numbers, so I'm just copying the structure that's immediately above the one that I'm drawing here, since I congested that up a bit. So we've gone ahead and drawn in our assignment here of 1, 2, and 3. And what will be the case is if you would rather not have to fuss with redrawing the molecule, what you can do is, with the lowest ranked group pointed toward you, which would be the case in this molecule, our hydrogen is pointed toward us, if we go in and assign the directionality 1 to 2 to 3, then, and the hydrogen points toward us instead of away from us, what that implies is that the arrow orientation is opposite what the actual stereochemistry is. So here, the arrow is going clockwise, but the orientation of the molecule has to be S, because the lowest ranked group points toward you rather than away from you. So what you can do as a trick or a hack is, if you don't want to rotate the molecule around to try to come up with whether the molecule is R or S, you can instead leave the molecule as is and recognize that if the hydrogen or lowest ranked group points toward you rather than away from you, then whatever you come up with as your arrow orientation, the actual stereochemistry has to be opposite that, since the hydrogen is in the opposite orientation of what the definition specifies. So in the next segment, what we're going to do is look at some additional examples of going about assigning RS stereochemistry.